So we're firing a bullet straight up. 850 meters per second is the initial velocity. I think we did a question almost identical to this in one of the first chapters, where we used a kinematic equation to find the final height. But here we can use another approach using the conservation of mechanical energy. And again, we're going to pretend there's no air present that would slow down this bullet, because that would use up some of the mechanical energy and turn it into thermal energy because of that friction between the air and the bullet. But here we can ignore air and make the approximation. We can kind of think about it and realize that the potential energy at the top is going to be equal to the kinetic energy at the bottom, because all of that kinetic energy that it had is going to get converted to potential energy, gravitational potential energy, as the bullet climbs. So the potential energy at the top is the mass times the acceleration of gravity, which is essentially the weight times the height that it attains. And there, h, there's our variable that we want to solve for. And so we can set that equal to the expression for kinetic energy. And then we just solve for h by dividing both sides by mg. And we can see the m's cancel. It doesn't matter how massive our bullet was. And we can put in 850 for v here and square it, and then 9.8 for the acceleration of gravity, and find the height. But this is really a sloppy, kind of shortcutty way to approach this problem. What we really should be saying is that the total energy, total mechanical energy at the bottom, equals the total mechanical energy at the top. And when we do it this way, it allows us to solve a bigger variety of problems that may be more complicated. Maybe the question is, how high is the bullet when it's only going 100 meters per second? So if we expand our equation, we can solve these more complicated problems, such as maybe the bullet goes up a certain distance and then compresses a spring and comes to a stop. So we should include in our potential sources of mechanical energy at the bottom, its kinetic energy at the bottom plus its potential energy at the bottom. Maybe it was shot from a certain height above the ground, and its elastic potential energy. So account for both gravitational and elastic potential energy at the bottom. So that would be the energy total at the bottom, and then the energy total at the top would be whatever kinetic energy it has at the top left over, plus its gravitational P at the top, plus its elastic PE at the top. So really this is the equation we should be using, and that'll allow you to solve a harder sapling problem too. But in our simple case, most of these terms are going to end up being zero. Since the bullet's shot from the ground, we'll just call it an initial potential energy of 0. It's not in a spring, nor does it ever compress a spring or stretch a band or anything like that, so it never has any elastic energy. And we're talking about the point at the top of its flight when it comes to a complete stop, so the final kinetic energy is 0 at the top. So, we end up with the same thing. Kinetic energy at the bottom equals potential energy at the top. But this is a more thorough, more exhaustive, and technically correct way to approach the problem. Just to be thorough here, these all disappear. The Ke at the bottom is half mv squared. The Pe at the top is mgh, and then we just solve for h.